Hello everyone. In last lecture, we have studied S-domain description for LTI systems. In this lecture, we will discuss the transfer function and the system properties. It includes transfer function and the system impulse response, transfer function and the system frequency response, and transfer function and system stability. The transfer function can be described in this equation. This is called pure zero gain form. Here, Z1, Z2, and Zm are zeros. P1, P2, and Pn are pures. K is a constant. We can depict it in this pure zero plot. Circle is the zero, and this cross is a pure. For example, the pure zero plot for h of s is shown in this picture, and we have known the h infinite equals 1. Find the transfer function for this pure zero plot. From the picture, we can find there is 1 pures and 1 zero. As h infinite equals 1, we can get the constant k equals 1. Because there is 1, 0, 2, and 1 pure minus 1, we can get the h of s equals this expression. Now we will discuss the impulse and corresponding the h of s. For the simple pulse at sigma axis, we can get its impulse response in this picture. For this pole, we can get its impulse response is in this signal. For this pole, we can get its impulse response. For the conjugate complex poles, we can find its impulse response in this form. And it's the impulse response. For this conjugate complex poles, we can get its response Ht. For this conjugate complex poles, we can get this signal. Now we will discuss the frequency response Hj omega corresponding to h of s. For a stable system, we can obtain frequency response Hj omega in this equation. We should know the system must be stable system. We can use this equation. For example, if the system is a stable system and its h of s equal s over s plus 1, we can get its frequency response Hj omega is this equation. So, if Hs is in a pure zero gain form and the system is stable, we can get the frequency response in this equation. Now we'll give the necessary and sufficient condition for a LTI system is stable. If the ROC of transfer function h of s includes j omega axis in S-plane, the LTI system is stable. Because this region of convergence includes j omega axis, so this system is stable system. This system is also stable system. This system is not stable system because the region of convergence doesn't include j omega axis in S-plane. For example, analyzing the stability and causality of the LTI system according to its region of convergence. This Hs can be expressed in this fraction form. For this transfer function, there are two simple poles. One is -1, another is 2. So for this transfer function, there are 3 possible regions of convergence. One is real part of S greater than 2. One is this region. Another is this region. So from the region of convergence, we can know only for this region of convergence, the system is stable. For this region of convergence, the system is unstable and causal because the h of t is a causal signal. For this region, the system is stable and non-causal because the signal h of t is two-sided signal. For this region, the system is unstable and non-causal because ht is left-sided signal, so the system is non-causal. So for arbitrary LTI systems, if the region of convergence for Hs includes j omega axis in S-plane, the LTI system is BIBO stable. If the system is the LTI system and causal system, we can use the poles to determine its stability. If all poles of h of s are located in the left half of the S-plane, then the LTI system is stable. For example, we have now the system are causal system and LTI system. To determine the stability for these systems, as the systems are causal systems, so we can determine the stability according to the pole locations of h of s in S-plane. For this transfer function, it has poles at P1 equals -1 and P2 equals -2, both poles located in left half of the S-plane. So the causal LTI system is stable. For this transfer function, it has poles at P1 equals -j omega 0 and P2 equals j omega 0. So these poles are not located in left half of the S-plane. So the causal LTI system is unstable. Here is another example. For this causal LTI system, determine the transfer function system differential equation, impulse response, and its stability. We can get the unilateral Laplace transform for this zero-state signal and input signal. This is y, zs of s. This is xs. According to the definition of transfer function, we can get the transfer function, hs. There are two poles for this function. This number should be the largest real part of the poles. According to the transfer function h of s, we can get the S-domain description of the system. By inversion of Laplace transform, we can get the differential equation for this system in time domain. By partial fraction expansion of Hs, we can obtain this equation. By inversion of Laplace transform, we can get the impulse response for this system. As the poles are located in the left half of S-plane, so for this causal LTI system is stable. In this lecture, we have studied the transfer function and system properties. That's all for today. See you later.